more reasons why it's very, very important that you understand that the logarithmic function, reason for existence, is to be the inverse of the exponential. And where this comes into play is not only so that we can graph them, but it allows us to solve problems and then eventually applications. All right, so just a reminder, the concept of inverses and logarithms. So the first picture is actually the one that I graphed earlier in the notes. All right, so there was my 2 to the x exponential function, and then its inverse, which would be log base 2, and again, it does reflect perfectly over that line y equal x. And then this is the exponential, and remember, when it's the ln of x is just the shorthand for log base e. That's what ln of x. It is called the natural log. Right? The natural log means its base is the natural number. So when you see that ln, it's the shorthand for log base e. And so the log base e is the inverse of the exponential function base e, right? There's the red function drawn here is the exponential base e. Its inverse is the natural log of x, which the natural log of x is the log function of base e. Since it's a common log, and it's a one that occurs in nature with Euler's number, we give it its own name and its own notation, and it shows up on every single graphing calculator, because again, it's one of the most common logarithmic functions we use. And so you'll look here, and some properties that kind of go with the inverses and logarithms. So again, they're reflected over the line y equal x. Exponential growth has rapid growth. Logarithmic has slow growth. So if it's the growth case, right, they're both growing, both the exponential and its inverse, the log. The log just grows a lot slower than the x. Whereas exponential is growing a population that's growing really fast. A logarithm, its inverse, is a population that's growing really, really slow. So slow sometimes it's hard to even tell it's moving. Some important properties that come from the fact they're inverses. These are the inverse properties. This actually comes straight from the inverse. F of f inverse of x gives me out x, or the other way around. F inverse of f of x gives me x, right? That's the test for inverses. Well, I already know logs and exponentials are inverses because the way the log was created was to be the inverse of the exponential. And so we know these properties hold true. And so that's what this is. This is just stating that property. If I take the log of the exponential, well, the log undoes the exponential and will leave me with x, and the other way is true too. If I take an exponential, raise it to the log of the same base, so if you notice there, both of these are base a's, the log and the exponential undo each other and leave me with the x value. And so some simple examples, we'll just start off with a simple case. So if I've got log base 10, which we usually just write log, so I'm just going to write that log, of 10 cubed, well, that's going to leave me with the 3. And if you, again, type in your calculator log, this is base 10, it should make sense because it's 10 cubed equals 10 cubed, right? But it holds true whether it's 10 cubed or not. If I just have log of 10 to the x, well, it gives me out x. It solves for x. So log base 10 of anything, because this is base 10, 10 to the x gives me out 10 to the x. Right, the other way is true too. If I've got 10 raised to the log of x, it's going to leave me with x, because the log, and this one's a little weirder in this direction because I can't really rewrite it as well, other than just going to the logarithm, so I'm actually not going to rewrite it because I think that confuses students. But just know the log base 10 undoes the exponential because they're, again, these two things undo one another. They do the opposite. They kind of cancel each other out when you're graphing. And so it leaves you with the x value. So it's 10 raised to the log of x, right? The log of x is log base 10. So if I had 10 log of 5, the answer comes out 5. And if you typed it in the calculator, 10 raised to the log of 5, you should get a 5 back out. And that's true for any base. All right, so I've done some examples of base 10. Well, that would be true for any base. if I had log base 4 of 4 raised to the negative 2.3, well, the answer that would come out would be negative 2.3. Or if I had e raised to the natural log of 2, well, the answer to that is 2, right? Because the natural log, remember, that ln means e to the log base e of 2. And so log base e is the inverse of the e function, and so they cancel each other out. And if you type this into the calculator, e raised to the natural log of 2, it should give you 2 out because they're inverses. Same thing if I wrote it the other way around, natural log of e squared. Same thing. Give you out 2. And so again, that comes from the fact that they're inverses. I think the book has a problem like this I wanted to do one. Log base 5 of 5 raised to, so log, so 5 raised to the log base 5 of pi. Well, the 5, the log base 5 cancel each other out, and so the answer to that is pi. Alright, so again, that's some properties of logarithms. If I write it the other way around, log base 5 of 5 to the pi, I'm still going to get pi back out. And again, why this works is because it's this inverse property, and we're going to use that when we go to solve equations. And so I've kind of been talking about our common bases, and we're going to get into the common bases in the other one. So again, this is just the property of inverse, the fact that they're inverses, and so they undo one another. This is the big property here about the fact that they're inverses. All right, so they undo one another and leave me with whatever's side. Again, it can be even more complex than just a number inside. If I have the natural log of e raised to the x plus 2, I'm left with x plus 2 out. Or if I write it the other way around, something like 10 raised to the log of 5x squared minus 3. Well, the log, base 10, this is understood to be base 10, and 10 leaves me with a 5x squared minus 3. That equals the 5x. And so that's where we're going to kind of go when we eventually get to solving the equations. We're going to use that. All right, we'll stop there. The next thing we're going to do is talk about, I've kind of been talking about them, again, the natural log and the base 10 are frequently used in change of base formula. I'm going to get to that in the next video.